Hello, my name is Joel, and I'll be presenting our work Auxiliary Tasks and Exploration Enable ObjectNav. Object navigation tasks an agent with searching for and stopping at an instance of a goal category, such as a stool, in an unseen environment. This agent is provided RGBD and GPS and compass sensors for localization. Our work investigates how we can accomplish ObjectNav through large-scale RL training of neural agents with generic architectures. That is, an agent which embeds its observations, concatenates them, and aggregates them in an RNN. This kind of agent nearly solves a simpler embodied navigation task called PointNav through a large-scale training technique called DDPPO. However, in ObjectNav, naive scaling leads to only 6% success rates. This has led previous efforts, including both of the winners of the previous iteration of the Habitat ObjectNav Challenge, towards semi-analytic agents with map-based policies. We aim to re-enable generic agents. In early experiments, we noted sample inefficient learning and poor exploration as key failure modes. The neural agent is not endowed with neither the tools nor the incentives to perform ObjectNav. To remedy these problems, we make a few modifications to the standard CNN and RNN architecture. The architecture is overviewed here. It still embeds observations on the left and aggregates them into recurrent cells in the center. The central recurrent cells are split instead of a large RNN, as this was shown to be effective for incorporating multiple auxiliary tasks in PointNav. This architecture was used to improve both success and efficiency over prior state of the art. Toward success, we use 6 distinct self-supervised auxiliary tasks. These tasks build environment and action models and thus improve sample efficiency. We also incorporate semantic features, both directly through semantic segmentation and through a semantic goal exists feature, which indicates how much of the frame is occupied by goal categories. In analytic policies, for example, similar features are used to explicitly decide when to navigate towards a cited goal. Note that segmentation is taken from the ground truth dataset in training and inferred from RetNet models in evaluation. We also use a count-based exploration reward to encourage the exploration skill critical to ObjectNav. The default reward, which only encourages progress towards unseen and unknowable goals, is much harder for agents to learn with. Notably, however, adding coverage reward can cause the agent to dawdle instead of stopping efficiently. To counter this, we attach a second policy, which only receives ObjectNav rewards and learns off policy throughout much of training. Eventually, we let this tethered policy act and learn on policy for a short period of fine-tuning. Here we show our agent successfully navigating towards a couch in the environment. This policy was provided an exploration reward and goes around the ottoman instead of stopping directly after sighting the couch. After switching to the tethered policy provided only the ObjectNav reward, the agent stops directly at the couch, raising navigation efficiency. We quantify various agent failure modes in our paper. Here we highlight sensitivity to semantic segmentation by showing an agent with look up-down actions in addition to the basic standard action suite of moving forward, turning, and stopping, performing the same episode with and without ground truth segmentation. Naturally, providing RedNet segmentation instead of the ground truth to the agent degrades performance. But interestingly, this up-down agent appears more sensitive to RedNet segmentation than the basic agents, qualitatively becoming much less consistent and skillful in its movement, as demonstrated in the bottom clip. Quantitatively, even though up-down agents are better than basic agents with ground truth segmentation, basic agents beat up-down agents with RedNet segmentation. However, upon fine-tuning the agents with RedNet segmentation, the up-down agents again beats the basic agent. This rank reversal suggests that this vulnerability to unstable segmentation is a learned property, and that the agent can appear to avoid learning robustness to segmentation by looking up and down when training with ground truth. The shortcut suggests we need to find ways of robustifying neural agents to noisy semantics beyond what standard gated cells are naturally capable of. Thank you for listening. Please check out our paper for analyses of RNN dynamics, in addition to some other investigations into our agents.